International. And the topic of presentation is Breakline collection from aerial LiDAR data, challenges and solutions. So this topic is slightly different from the earlier presentations, because whatever I'm going to talk about is one of the input that goes into the GIS analysis. And as you all know, your model or your analysis will be good, provided your input data is good. So to that extent, I think my topic will address that issue, how to create more sort of quality data that gets into your analysis. And as Paul presented earlier, one of the input he uses in his analysis is the DEM. And to that extent, I think my topic will cover more on the LiDAR, as well as the quality of the product that you can get from the LiDAR. So this is the agenda for my presentation. Quick overview on the LiDAR technology and the workflow for those who are not familiar with the LiDAR. I'm sure most of the people who are present here are well aware of the LiDAR technology and the products that you can get from LiDAR. And I will talk about what is the Breakline and how do we collect Breaklines from the aerial LiDAR data. And the next the topic will be the challenges and the solutions in terms of collecting Breaklines from the aerial LiDAR. And also I will talk a little about the software which Baker has developed in-house in validating the Breaklines. And finally, of course, I'll be open to any questions. So just a quick overview on the LiDAR. It's a proven technology, specifically for topographic mapping. It's light detection and ranging. By simple definition, it's billions of recorded points collected and processed to create a three-dimensional representation of the border and features on the Earth at centimeter level accuracy. And of course, that is constantly changing from the aerial LiDAR, where you can get centimeter level accuracy, to mobile LiDAR, to static LiDAR. We have now gone below the centimeter level also. So as the technology progresses, you get better accuracy from the LiDAR data. So this is the a simple snapshot of the aerial LiDAR system components. Basically, it has the LiDAR sensor, which basically transmits the light signal and collects. And you have got the GPS to provide the accurate position, XYZ. And it has an inertial measurement unit or the navigation unit for the attitude. So together with the GPS and IMU, you get the 6 parameters, which is X, Y, Z, and pi, omega, kappa, to precisely tell the position. And so there will be a GPS will be stationed near the area where the data is collected, which is primarily used for calibration purposes. So this is, in a nutshell, about the aerial LiDAR system components. So this is a pictorial workflow in a very, very simplistic manner. You fly the aircraft, collect the LiDAR, and once you collect the data, you will have 3 different inputs. One is the range information from the LiDAR sensor. You will have the XYZ information from the GPS, and you will have the pi, omega, kappa from the IMU. Together, you bring all the 3 data sets together to create what we call it as a point cloud. Point cloud is nothing but a stream of points with the XYZ values, and that's what we are seeing on the second imagery. And once the point cloud will have points or the reflections that come out from the ground, as well as the non-ground features like trees and etc. Then you go through the processing. That's where the job comes into, and you classify the data into various classes like buildings, ground points, and vegetation, so on and so forth. And then once you have the ground points, you take the ground points and generate derivative product, including the grid, the contours, and so on and so forth. So there are plenty of derivative product you can generate once you have the ground points. So this is the LiDAR project workflow. What you are seeing on the left-hand side is the phase of the project lifecycle, and what you are seeing on the right-hand side is the various activities that goes under each of the phase. You start from the planning phase, where you plan for the aerial mission in terms of the pulse spacing, what sort of point density you have to get, what is the vertical accuracy you have to achieve, and what is the contour interval you have to get. And then, once these parameters are set, then you get into the collection mode. You collect the data and with respect to the specified parameters. And then the third stage is, of course, the pre-processing, and that's where, as I said in the earlier slide, you combine the range, the GPS, as well as IMU to create the point cloud. And the fourth stage is where the critical thing, that's a LiDAR data processing. And the first one is called the automatic and manual process. That is what it separates the ground points from the non-ground points. And the second thing is the breakline collection. That's what the topic of the presentation is, which I will talk more in the subsequent slide. And third is, of course, the extraction of features. So once you have the ground points, and once you have the breaklines, and then you get into the post-processing, that is where you create the derivative products. As I said, it can be the DEM grids, contours, and so on and so forth. And of course, the quality control is an integral part of any of the LiDAR project, and it is applied across each phase of the activity. So traditionally, when we call about DEM, which stands for digital elevation model, in any elevation technology, as I said, LiDAR is one of the elevation technology. It can be photogrammetry, it can be microwave-based sensor. So whether you use any elevation technology, there are two inputs out there. One is called the mass points, which is basically the ground points. The second one is, of course, the breaklines. The breaklines represents the terrain more closely. So now, when we say, well, then the basic question is, what is the breakline? What is a breakline? Before we get into the details of breakline collection, what is a breakline? Basically, breakline defines the break in elevation between two surfaces with different slopes, or describe a change in the smoothness or continuity of a surface. So basically, when you generate the derivative products like contour or the elevation grid, breaklines play an important role by which, so your product will represent the terrain as closely as possible. So to that extent, breaklines are very essential in any area LiDAR project. Now, the next question is, what are the different types of breaklines we can collect? In an overall picture, you can think of three different breaklines. One is the topographic breaklines, the other one is the hydrographic breaklines, and third one is the hydrologic structures. The topographic breaklines are, you know very well, those are all the roads, the edge of pavements. Those are all the things which we call it as a topographic breaklines. The hydrographic breaklines are primarily the lakes, ponds, rivers, streams, etc. And the hydrologic structure is primarily bridges, retaining walls, so on and so forth. So now the question comes, do we need to collect all the breaklines in any area LiDAR project? That's always a challenging question in any area LiDAR project. That depends on the requirement. So what is the ultimate purpose for which the product is going to be used? So if you know exactly what is the purpose for which the data is going to be used, then accordingly you can decide what sort of breaklines needs to be used. For example, in the case of FEMA-related application, especially if the data is going to be used for floodplain analysis and modeling, then naturally you need to definitely collect the breaklines corresponding to hydrographic and hydrologic structures. And if the data is going to be used for more towards the transportation or more towards the design level of application, then obviously you need to collect the topographic breaklines also. So this is one of the very critical component in any project planning. So ultimately you should know what is the ultimate purpose of the product, and accordingly you need to capture the breaklines. And the last point is, the breaklines along with the ground points define the contour behavior. So ultimately, as I said, one of the derivative product that you can get from LiDAR is a contour, and the contour should follow the terrain as closely as possible. So to that extent, breakline play an important role in creating the final products from the LiDAR data. So the next question is, what are the methods by which the breaklines can be collected? The proven method is the photogrammetric method that has been in use for so many years. And you can collect the breaklines from the aerial images. But now with the with the current trend, it is, it's very difficult to have both an aerial LiDAR mission as well as the imagery mission because it is going to add to the cost. So it will be two different missions, but of course nowadays we have sensors which can be placed along with the LiDAR sensor, so you can simultaneously collect the imagery as well as the LiDAR. But there are some issues are there with regard to that type of collection, because you cannot have a single parameter, especially the flying eye, that cannot be used for both the images as well as for LiDAR. So in essence, there is not, the situation is like that is that you will have only the LiDAR data. There will not be any availability of imagery to collect the break lines. So what happens is that you have to depend on the aerial LiDAR to collect the break lines. So when we go to the aerial LiDAR for collection of break lines, we use what is known as the technology, what is known as the LiDAR, which is somewhat similar to the photogrammetry. It uses the photogrammetric software for feature collection, especially the breakline collection. And the LiDAR intensity returns are used to create raster stereo pairs. And the absolute orientation solution born from LiDAR data. In the sense, this is somewhat similar to an aerial photogrammetry project. I will talk about this LiDAR grammetry in the next slide, just to bear with me. And the other way of collecting the break lines is, what we call it as a 2.5D. That means straight away you do the digitization from heads up without getting into the LiDAR grammetry. There are some advantages are there, but there are some disadvantages there by collecting 2.5D break lines directly from the LiDAR intensity data. So what is LiDAR grammetry? This is one of the, it's sort of complementary to the photogrammetric technology. And the people have known the photogrammetric technology people have used photogrammetric technology for years. In photogrammetry, what we do is we take two images, which are primarily 2D images, and create a 3D perception. What we call it as a stereo pair, okay? And then we use the stereo pair to collect the 3D points. Whereas in LiDAR grammetry, the process is reversed. What we do is we create a 3D images from the LiDAR data, and what we call it as a reverse sort of a pseudo stereo pair, and then we take the data to the photogrammetric workflow and collect the break lines, just like as we do in the photogrammetry. So what happens is more or less all the tools we have used in the photogrammetry, we can use in the LiDAR grammetry also. And the last point is very critical, features are orthographically correct. So that's one of the important things in a LiDAR grammetry process. So now, what are the challenges in LiDAR grammetry? Just like photogrammetry, there are some challenges in there, and we have encountered such challenges, and we are able to work through some of the solutions. The first one is the dense vegetation. Just like the images, if there is a dense vegetation is there, you cannot see the ground. So in the same way, there is a dense vegetation it will play a role in the case of collecting the break lines from the LiDAR intensity images. And then the second one is the radial distortion, which is the leaning of trees and buildings. And the third one is, of course, the surface reflectance. We are using a reflectance as an intensity to create the images from the LiDAR. So that will also play a role in the case of collecting the break lines. So what happens is in dark areas, the compiler tends to dig in elevation, whereas in light area, the compiler tends to float. It means when you say dig or float, it means you are not exactly measuring the ground point. So that means whatever the value you get from the breakline capture, either it is off, either it is above the actual value or below the actual value. That's what it means by dig or float. Okay. Now the other challenges with the LiDAR grammetry is, as I said earlier, you will not be having the current imagery. So you have to live with only the aerial LiDAR to collect all the information that is available or that is possible from the LiDAR data. And some of the, in difficult terrain conditions, capturing the shoreline is very difficult. And the third point is because of frozen ice at the edge of the shore, you'll be wondering why this particular point, because as a company we have done large projects in Alaska, and the terrain conditions are very difficult. The window for data collection is very limited, And so with all these challenges, we have learned some lessons as we work through very big projects for pipeline-based corridor projects using aerial LiDAR. So we learned some lessons. In that process, we are able to improve the workflow over a period of time. And so the last point is very critical. Even if a 0.5 foot difference, that means even an half foot difference in capture, that will play an important role in the final product. So that means our breakline capture should be as accurate as possible so that you get a very good final product. So what are the solutions we learned is, the first point is, when we get the point cloud, we have the, as I said, the point cloud contains both the ground points as well as the non-ground points, okay? When I create the intensity image, I can create two different sets of intensity image. One is directly from the point cloud. That means my intensity image will show both the ground features as well as the non-ground features. That's one set of product. I can use it in the radar telemetry. The second product will be, I can classify the LiDAR data. That means I can go through the process of automatic and manual extraction of ground points. And once I create the ground points, and then I can create the intensity image from the ground points. So I can create two different intensity images, one containing both the ground and non-ground points, the other one only containing the ground points. And we use them both during the radar telemetry breakline collection process. So, but of course, it will take a little more time, but that is the price you pay in order to get a better product. Then what we do is, the advantage of doing both the ground points as well as the non-ground points imagery is, if once we have the ground points classified and then you create the intensity image, then what you can do is you can generate the contours immediately with the ground points. So at the time of collection of breakline, the compilers will have the additional tool of the contours, so that they can see the terrain and add the breaklines where it is needed, whether it is the hydro breaklines or the transportation breaklines. They can add the breaklines where it is needed, and also they will be very accurate. And the other important advantage is with the LiDAR data is you can create cross-section profiles and make sure that the breakline exactly follows the terrain. So these are all some of the tools we develop as we go through the compilation of the breaklines. So this is one of the examples and of the challenge we face in some of the difficult conditions. So if you just see the left image only, without having any other imagery, what you are seeing in the left-hand side is the LiDAR intensity data. You may tend to think that the black line is what the sort of lake or a pond. So you try to draw the line, but in reality on the ground, what you're seeing is not a water body actually. And this is one of the very difficult terrain, very close to the area is called Kotzebue in Alaska. And as you can see, the GPS controls have been activated through an helicopter-based. So people have to fly through the helicopter to get some controls which are needed for constraining the LiDAR, also for validating the LiDAR. So this is the type of challenges you face in some of the pipeline-based projects. Especially the terrain itself imposes a lot of challenge in getting the necessary control, constrain the LiDAR, and also creating the breaklines. And this is another example of what you're seeing on the left-hand side. If you just go by the breaklines, if you just go by the intensity images and you correct the breaklines, what you are seeing are the blue lines, or what you have collected the hydro breaklines or the blue lines, and the other lines are the more like a terrain breaklines. So what you are seeing on the left-hand side is just by breaklines from the stereo only. But really, if you go through the breaklines from stereo, along with that you create the cross-section profile, you can see some additional breaklines have been added, which are the green lines in between. That makes a lot of difference in the final product. So that is the type of improvement of the production workflow efficiency that we are able to achieve by not only using the stereo imagery, but also using the cross-section profiles, by which we can improve the breaklines And as I said, so that the final product will represent the terrain as closely as possible. And this is an example of what is a cross-section profile. What you are seeing on the top left is the intensity imagery, and what you are seeing on the bottom is basically a cross-section profile. So the cross-section profile tells you how the break lines should be drawn or how the break lines should be added. And once the break lines are collected, then the next stage is, of course, the post-processing. And this is a sort of common challenge. Every user has got their own final product deliverable. Some people would like the product in AutoCAD, and many people would like the product to be in ARC. Whereas the production environment is primarily a microstation-based environment. So you make sure that the post-processing, what all the information you capture is properly translated. At the same time, you make sure that some of the standard GIS-related stuff like no dangles, no undershoot, no overshoot, so that the contours are clean files the end user gets. So this is some of the the post-processing challenges in terms of meeting the different client requirement in moving the data from one platform to another platform. With that, I get into the next stage. Okay, one is you collect the break lines. The next one is how do you validate the break line? That's more critical. We may use the best tool, but ultimately the data should be as clean as possible. So realizing the importance, Baker has spent money, invested money, and we have developed our own in-house tool to validate the break lines. So these are all what you are seeing on the left-hand side is some of the parameters or some of the points which the break line should meet. It's very obvious. All the vertices of a break line should have a Z value. That's a very straightforward thing. And the vertices should not have a 0 or null elevation. That's a very straightforward thing. The first point is very critical, that is a monotonicity, which means it's a very simple again. Any river or stream will always flow from a higher elevation to a lower elevation. So if you take the first topmost point and you take the next point, obviously the elevation of the next point should be lower than the previous point. Otherwise, this condition will not meet. And the last fourth point is more towards the hydrologic modeling type of thing. So we took all these inputs based on various specifications that are available, and then we developed a tool which will, basically it will take the point shapefile as an input, and it will perform the vertical consistency check as well as the monotonicity check, and it will create a report. So this is an in-house tool we developed without depending on any toolkit or anything. It has been developed from scratch. And then, this is the interface, user interface for the program, wherein you can give the breakline file. It will create a report, and also you can give the whatever be the tolerance, depending upon the contour interval you're going to generate. You can give the tolerance value. And once you give the inputs, the program runs and it checks both the things. One is the vertical consistency, telling you how far the break line is off from the LiDAR surface, number one. And also, in the case of rivers and streams, it makes sure the river flows from a higher elevation to a lower elevation. So that is what the software does. It validates both the things. It will throw you two reports. This is one report. The other one is the vertical consistency report. And you can take these two reports. You can go back to the break line. Wherever there are errors, you can fix those errors. That way you can get a very clean break line file. And once you have the break line and you have the ground points, and then you take these two inputs to the post-processing or the production thing, wherein you can create the derivative products like the grids, contours, and so on, other products, whatever that can be generated. So I believe with this, it ends the presentation. I'm open to any questions.